Because the thing we were doing a lot more at the start of class, which we haven't done in a bit too much, is like electric fields from point charges, but that's definitely, part of this. And so an even problem that I recommended from chapter 21, so this one, we can't check the answer, so I have to be right. So 2138. So here you've got a square, you've got a charge Q here, and side length A, I guess it is. And you've got another charge of plus Q here, and you've got another side, this is a square, charge minus Q down here, and then another side length A, and another charge of minus Q down here, and there's a side length A here. And I think the question is to find the electric field at the origin, assuming it's in the middle. What is the direction of the net electric field at the center of the square due to the 4 charges, and what's its magnitude in terms of Q and A? All right. Again, I'm still annoyed I didn't get the answer in the last one. I'm having a bad day in terms of crunching numbers. So, all right. So what I do in this kind of situation is I label things. And I use the principle of superposition. So labeling keeps me straight, So I'm going to call this one like 1, 2, and then, this is Q3, and this is Q4, okay? So Q2 equals to Q, Q1 equals to Q, all right? And then I'm going to label the corresponding electric fields E1, E2, E3, and E4, right? So E1 and E2, they're both positive charges, which means that the electric field goes radially away. So E1 is going to go like this, right? There's your E1. E2, it's going to go like this, right? Radially away. And how about the other two? I'll do them in red. Did I ever move the camera? I don't think I did. Uh-oh. I wonder if I ever moved the camera. I get lost sometimes. Oh no, I do have record of my bad somehow flawed calculation over there. Who knows? I bet the calculus is okay. All right, so how about the negative charges? I mean, I wish those negative charges were positive. Then it would be easy, right? If the negative, what would it be? It'd be 0, right? If these were plus, then this would be like this, and then like that, and 0, but they're not. So they're like this, right? So it's there's your E3, and this one would go like that, right? This would be E4. So basically what I'm saying is E1 is parallel to E4, and E2 is parallel to E3 in this situation. But you can also see from the symmetry of this problem that the horizontal pieces cancel out, right? The net electric field should be vertical and downward. So to calculate the net electric field, we just need to find the vertical component of each one of these guys and add them, right? But it's also fairly clear that the electric field should just be, well, let me just say it this way. The electric field should be equal to 4 times, I don't have a good notation for it. The electric field should be something of the form basically, well, find 0, comma, minus E, right? Where E is the magnitude. I haven't said anything especially interesting. What I'm trying to say is if we could quadruple.
Yeah, I see what you mean. If you take cosine of 45 degrees and you make like a straight line.
Cosine of 45 degrees times like any one of the E's. We'll say E1 for good measure. Oh, yeah, fair enough. So we say, so this, 4 times this times the K, QQ, right? Because, oh, we're finding electric field. We don't have a QQ here, right? So KQ, that was a force problem. That's why we had QQ. This is an electric field problem. So if kq over the distance squared, right?
Just like the square root of 2.
Okay, so we got what? We got 4 divided by the square root of 2 times, I don't know if it's 1 in terms of epsilon. Oh, this is an even problem. We can't check. So 1 over 4 pi epsilon naught and q, and you just told me that the r was actually, oh, I got to
Square
be,
root of 2 times a.
are you thinking about it like this? Is it, like, I'll draw it like this.
Triangle, and then
See,
I
because,
didn't think about it like that.
yeah, I was going to get sucked into that too. So
I was
the
about to do half of them, yeah, okay.
so the distance, this is the r, right? So like I can't draw r today. R. So yeah, r should be like r squared is a over 2 squared plus a over 2 squared, right? So like that's
Yeah.
a squared over 2? Man, that looks wrong. I think it's
Square root of 2 over 2.
that looks wrong. That looks wrong, but it's right, you know.
Yeah.
But
It's incorrect. That's square root.
okay, so oh yeah, so it's, what do you say it was? It was a over root 2. Yeah. Of course, we want r squared here anyway, so we might as well just put a squared over 2 down there, and then, you know, I guess I could clean this up. We would have, if I put the 2 up there, I've got 8 over 4, which is 2. So I think I get q over 2 square root of 2 pi epsilon naught a squared if I didn't do something wrong, which of course you could also write in terms of k. And if I was to word this problem and be so foolish as to not fix, if I give this kind of problem on the test, if I'm smart, I'll say, please leave your answer in terms of epsilon naught, or please leave your answer in terms of k. Otherwise, my grading becomes slightly more complicated because I need to look out for both, you know. So.
Where did you get the electric field equals 0?
So, where did I get the,
Right?
oh, this?
Yeah.
Just like the geometry. So like look at it. The horizontal pieces cancel, right? So it's got 0x, and it's got to be just downward. And then we were thinking about it. It's the same downward component all 4 of these have. So we just did 4 times cosine of 45 times the magnitude because it's a 45-degree angle to pick out the, you know, the adjacent side to that 45. We can do that. So this is again, you know, by the picture is what's motivating this. I haven't really explained that, but you know. Maybe I should just work even problems. Why didn't I just assign even problems? If I assign even problems, then I can't be wrong. How about 59? Have we done that one? 2159. I feel like I've done a lot of Gauss's law in class, not as much of this stuff. This might be a good one to work out. 59. Let me look at 69. I think 69 is very much related to an example we worked in a previous help session. So I'll leave that there. It does have 3 dots, but I worked out the arbitrary equilibrium problem, the other class, the other help problem session. 59 might be kind of a good stopping point for us today. We'll try 59. It is an odd problem, so I'm slightly concerned, but it's going to work out. It's going to work out. I just won't crunch the numbers. I'll just write down the number from the answer key and pretend that's like what the calculator gives. Then I can't be wrong, right?
Yeah.
So.
Someone checks that out.
Yeah, imagine if I actually edited videos. I could always be right. you know.
Put a green screen.
That'd be fun. So 59, we've got a 5 nanocoulomb charge is placed at the origin of an XY coordinate system. I really hope it's a two-dimensional problem. So we've got Q1 here at the origin, 5 nanocoulombs. And Q2 is on the positive x-axis at 4. And it is we're told it is minus 2 nanocoulombs. And we have then we're told a third charge, Q3, is now placed at x equal to 4, y equals to 3. Oh, this is more the kind of problem I wanted. Oh, where was this that I just said? This is at x equal to 4 centimeters. All right, and we're told that third charge Q3 of 6 nanocoulombs placed at 4, 3. So it's like up here, Q3. And we were told 6 nanocoulombs. And this is the point 4, 3 in centimeters. All right. We're supposed to find the total force exerted on this charge by the other two. And then we're supposed to find the magnitude and direction of this force. This is actually a great problem. This right here is like smack dab down the middle of like a nice kind of friendly, moderate test question. This is really nice. This is a nice problem because it has a good test of whether or not you understand Coulomb's law, and it's also got a little bit of vector analysis, which is something I expect students to have at this level. So, yeah. So we want to find the net force on Q3 due to Q1 and Q2, I think I said. I've already forgotten the problem. That's not a good sign. Yeah, on the third charge by the other two. So, all right. So I'm going to mess up my picture a little bit, but F1 is like this, right? And F2 is like this, right? Yeah. But we have, I mean, you can fall back on the formulas I shared with you guys in like the first couple days, or you can just kind of reason it through geometrically and the magnitude coming from the Coulomb force. We'll do the geometric magnitude thing here. I think it'll be fine. So let's see here. F1 is equal to, I guess I'm going to fall back on my formulas actually, because that's just how I am. So I'm going to do K, Q1, Q2 divided by, what's the distance here? I should call that R1 probably. So like script R1 we could call, what's that? What did I do? Oh yes, thank you. I was trying to find an error over here, but you're talking about over here. So I was like, wait, what? Cool. So this is the vector, right? The displacement vector from 1 to 3. I do 4 over, and well, it's actually just 4, 3, isn't it? Right, and 5 centimeters is magnitude. Oh, cool! It's a 3, 4, 5 triangle. Yeah, it is indeed awesome. I should make all of my problems like that. So we have got 5 centimeters cubed down here, and then we can do, 4, 3 centimeters up there. If you don't, well, I'll leave the centimeters on. It's really, I hate units. Tell you what, I made everything a symbol. You use symbol? Yeah, that's not a bad idea. Yeah. I'm going to just convert to meters. Like this is going to be, good grief. Yeah, let me, I'm going to just let L equal a centimeter just because I'm tired of thinking about this and I'm tired. So that's going to make this 4L, 3L, and that's going to make this, you know, 5L cubed down here. Great. Fine. Now I'm free of the centimeter business. And how about F2? So if you guys know what I'm using. I fall back on this sometimes if I'm tired. If I'm more clever, I'll go back to like, you know, geometry and just doing stuff like the book does. But this is actually when I'm lazy, I do this. All right. So what you got is, you know, r squared. You can do an r cubed times r vector, and that's a formula for the Coulomb force. And just make sure the r is pointing in the appropriate direction when you set it up, all right? Okay, so F2, my r is what? I mean, if r goes, I want to think about r being like that here, you know? So, this distance is just 3L, right? So I've got K Q2 Q3 divided by 3L cubed, and it's downward, right? It's supposed to actually be 0 minus 3L. Listen, you don't have to do it the way I'm doing it right now. You can figure out the magnitude of each of these forces and then do trigonometry to add them together. Like that's also totally legitimate, and it might be faster, right? This is just my default way of thinking. So if you don't like it, do things the way the book does. I'm sure the book just finds magnitude and does angles and breaks things into components, you know? But now we superposition, add the forces. I was supposed to find force, right? This is a force problem? Okay, good. So net force is F1 plus F2, which it looks like I guess we can write K over, there's a net of like a K over L squared in all this, right? And then I can do like 4 Q1 Q3 divided by 125 comma 3 Q1 Q3 divided by 125. It's almost certainly better to just put numbers in at some point here. 3 divided by, looks like we got a Q1, Q2, Q3 divided by, I think that's a 27 there. Yep. So I should crunch the numbers, I suppose. What's that give me? 9 times 10 to the, okay, so L was a centimeter, which is 0.01 meters. So when I divide by 0.01, that means I'm multiplying by 100. So that's multiplying by 10,000. So I think that should be 9 times 10 to the 13th, if I did it right, which is very debatable at the moment. So that Q1 and Q3, 5 times 6 is 30. So I've got 30, so I've got 120 over 125 if I did that right. But I've got times 10 to the what? nano, which is 10 to the minus 18. And 1 times Q1 times Q3, so that's 30. 30 times 3 is 90. 90 nanocoulomb, so 90 over 125 times 10 to the minus 18. I should just let you guys calculate it because I'm not going to get it right. It's just impossible today. And I already put the minus in terms of choosing the direction, so don't put in Q2 as minus 2. I accounted for that in the formulas already. That's 12. 12 times 12 over 9. Well, 3 over 27 is 9. 9, so 12 over 9. 12 over 9, that's something, isn't it? I'm just going to write it as 12 over 9 because I don't want to think. So 12 over 9 times 10 to the minus 18 again. So I've got a 10 to the minus 18 everywhere, so I can rewrite this as like 9 times 10 to the minus 5. And then I've got a 120 over 125 and a 90 over 125 minus, I think that's 4/3, yeah? Yeah. Now, like I said, you don't have to calculate like I'm calculating. This is just my way. It's not a good way. It's just a way. 24 over 25. Well, thank you, useless calculator. Let's get a decimal here. 0.96 times 9. So, all right, 8.64 times 10 to the minus 5 for the x component. If I did it right, I should just let you guys do it. Let's face it, I'm not going to get it. I know, right? I'm the worst. Oh, that just makes it worse, right? All right, so minus minus 5.52 times. It is so true, though. That attitude will be a self-fulfilling prophecy. But fortunately, whatever points I lose, I can just take back from you guys. So there's that. So I get 8.64 times 10 to the minus 5 and minus 5.52 times 10 to the minus 5. Of course, that's, if I've done everything right, that should be in newtons. That's what you got? Woohoo! I think, what did it tell us? To find the x and the y components? Is it what the book has? We did a problem right? Yes. And so one more thing and then we're done.
You should just put this one on the test.
Just put this one on the test. I'll have to change the numbers. Otherwise, I'll just get people writing down the answers like that counts. Why do people do this? Like, it's not, I want you to understand, just to repeat my answer, you know? I mean, it's good that they studied and copied the answer down. And it's even a worse problem. Oh man, tell me I didn't move the camera. I didn't move the camera. Well, that was very, very dumb. But par for the course in here. Sorry, people at home. But look, it's all here. I'll run back through it. What we did was we figured out the force from charge 1 and charge 2 on charge 3. So the force from charge 1, we take, the displacement from here to here is 4.3. And so we set it up over here, K, Q1, Q3 divided by, we let L be a centimeter to not have to write centimeters all the time. And that gave us 1 over 5 times, because it's a 3, 4, 5 triangle, so the distance is 5 centimeters. So 5L cubed, and then this is like my R hat. This is R over R cubed formula. And so that's the force from the first charge on the third charge. And of course the other one is a negative charge, so it goes downward, and it's purely vertical, and that's the formula for that. And then, so we have to take the vector sum of these to find the net force, and we did that calculation, and after some suffering, we got to this answer, which I'm told is the answer in the back of the book. Woohoo! And now that all that remains is to figure out the magnitude and the angle. Standard angle, I think. So the magnitude, F, is the square, well, we can do this. We can do 10 to the minus 5 times the square root of 8.64 squared plus 5.52 squared. And that's going to be newtons, whatever that works out to. I used to be really good at calculators, and then something happened. I stopped using it, I think what happened. So I got 10.25 times 10 to the minus 5 newtons, or maybe the book might write 1.025 times 10 to the minus 4 newtons perhaps. That's the magnitude. Are we also asked to find the standard angle? And direction. So let's find the standard angle. What's the standard angle here? Will that work? But is that okay? Like, let's picture it. Where is F? I'm not saying it doesn't. I'm really asking. So this force is in quadrant 4. So you were right. You're down here. That is the province of arctangent. Arctangent works when x is positive. So we really can do theta is equal to inverse tangent of the y component divided by the x component. That will work here. And it should be a negative angle. So we've got, and you can ignore the 10 to the minus 5s, right? So we just do inverse tangent of minus 5.52 divided by 8.64. Make sure you're in degree mode. That'll get you. We like degrees in here. This is physics. So I got minus 32.57 degrees. Does the book have that, or I don't know? Woo! All right. Well, you guys have improved my weekend significantly because we actually solved these problems correctly, so I feel much better about my day. But do not stress too much about the test. Just do your best. Everything will go okay if you have done the problems and understand them. If you finish a few more past the ones we've done in here, that'd probably be good for you. But if you don't have time to do all of them, do not stress. Just work enough that you have the ideas down, So have a good weekend.